Okay, so hi guys, once again, welcome to the tutorial. In this session, I'm just going to give a brief overview of the simulator. And then after this, we will do the three hands-on tutorials that Tushar mentioned about. So just a kind reminder that all the sessions of this tutorial is being recorded for anybody who has joined after the first session, just to keep that in mind when you are sharing your video or unmuting yourself. So with that, this is the agenda which I have for this talk. So I will go through why we do DNN acceleration, and this is probably just a repetition of what Tushar and Paul already talked about. Then I will go deep dive into the tool, what it does, how it models the compute memory and interface, how it models the different operations, the different mapping strategies, and the tools, inputs and outputs. So we model systolic arrays, and the choice for this kind of a substrate is we came up with this choice because we know that we require high parallelism. Systolic arrays provide that, and they also do that with a very simple implementation. And due to the forward peer-to-peer forwarding links, we have very high and efficient data reuse. And all of these together means that we can scale this kind of a substrate very easily. So the metrics of interest that we look forward in a DNN simulator are three, right? So we have to model the compute, we have to model the memory. And since accelerator works along with the host system, so we have to be cognizant about how we are doing in terms of the interface traffic, because that can affect performance as well. So obviously, when we model compute, we care about performance, efficiency, and scalability. In memory, along with performance and efficiency, we care about the reuse factor, which Tushar has talked about. And in the interface, we care about some system level implications and overall how the entire system performs when you integrate it. With that, let me go a little bit deeper into ScaleSim. So this is the same figure, the 10-foot view of ScaleSim which Tushar presented. So we have two inputs to the tool. One is a configuration file, which basically tells you what kind of hardware we are going to model and what its mapping is. So you can see the parameters over here. And then we have a topology CSV file, which describes the workload which is going to run on this particular hardware. And for each layer of the workload, because we are simulating a neural network, we get a cycle count, interface bandwidth, and ScaleSim also generates cycle accurate read-write traces from both SRAM and DRAM transactions. So a little bit more detail into the configuration file. So this is a dummy configuration file, and the configuration file basically has two sections. So architecture presets is what we are interested in. And in architecture presets, we describe the array microarchitecture. So since this is a systolic array, the only parameters which we care about are your array height and array width. And you can change this in the tool independently. So you can have arrays with different aspect ratios. For instance, you can have a very long and skinny array where your width, let's say, is 1 and your height is 256, vice versa, or you can have a square array like this. And then we have the memory sizes. So these sizes are in KB. So for instance, this particular configuration will have about 8 MB of storage for each of the buffer. And this includes the double buffered size. And then we have some matrix offset. So this is strictly to ensure that the operands which tool reports could be made sense of. So for instance, if you have an operand address, even within the range of this 10 raised to power 7 to 2 into 10 raised to power 7, we can say that, oh, this is an element of the filter matrix. And then finally, we have the data flow, which is basically the mapping strategy onto the systolic array. And I will go into details of what the data flows we support and how they look like. But this is just a small string notation, which you can tell the tool to what to expect. And then, so somebody asked about topology file, right? So yes, this is a handwritten topology file, and it looks something like this. So this is basically a list of network hyperparameters captured in a CSV. and we capture it in a layer by layer configuration. We have a bunch of CSV files in the ScaleSim repo so that you don't have to go ahead and make one every time you want to run. But for any network which is not there right now, unfortunately, you have to handwrite it. And like I said, that we have plans to make it automated as well. So now let me go into a little bit more detail on how we actually model compute. Like I said, that we support non-square arrays. So you give row and column inputs as row and columns as inputs to the configuration file. And there are multiple data flows. So we saw output stationary as one example. We also have two other base stationary and input stationary, and that essentially covers all the data flow space of systolic arrays on a high level. And the USP of ScaleSim, I would say, is that it is quite faster than if you look at other cycle accurate simulators. And the reason for this is partially that we are looking at systolic arrays, which are very deterministic. So we can capture the execution details by just tracking what is going in and out of the edges. And obviously we do a layer by layer execution so that you can reorder. I mean, it is independent on how you provided the inputs in your topology file. And then so one thing which I did not mention before is that often in our cases, we have our compute so large that it could not be mapped onto the array itself. So ScaleSim automatically takes care of that and intrinsically folds or intrinsically serializes big computes into smaller chunks and then schedules them so that the user does not have to worry about it. So on the memory side, we have double buffered memory. So we have three SRAMs which we can capture. And the double buffered memories work like this, that you have one buffer from which you read the data for your execution and another buffer where you prefetch the data. And due to reuse, what happens is that smaller buffer size actually is used for more computations than it would allow for if it was a streaming data pattern. So this is a standard practice in architectures like the spatial architectures like a DNN accelerator. And therefore, we just model the memory as in double buffer fashion by default. And then for each matrix, obviously there are there is a separate buffer for them. One, so any gem operation uses or convolution operation has two input operands, input feature map and filter, and then one output operand out to feature map. And we logically, like physically, you can implement them as a single double buffer, but in ScaleSim, we logically partition them into three separate entities. And then because of the native operation that is being supported in ScaleSim being convolution, we do not have to replicate any elements in the SRAM buffer. So there are two essential ways of modeling convolution. So one is that if you just model it as gem, so if you do that, then obviously you create the matrices, and in from a convolution, from this transformation from convolution to gem, the matrix elements get repeated because there is the sliding window pattern which Tushar has depicted. But in ScaleSim, the way we model it is that intrinsically we know that the controller of your microarchitecture is going to take care of that. Therefore, you don't need to store repeated elements in the memory. So after memory, we model the system interface as well. So the way we do this is that we keep track of the DRAM read and write bandwidths. So ScaleSim V1 actually just assumes a stall-free operation and tells you what the optimal read and write bandwidth of the interface should be to keep your accelerator working without stalls. In V2, we have added a new feature in which you can force the simulator to go into a stall and by providing a user specified bandwidth. But once you do that, you can see that, oh, if your interface is not generous enough, then you can get bandwidth limited very easily. And if you do that, what is the impact you have on your performance? Or if you are going the other way around, where you say that, oh, I have this simulator and these are the workloads which I want to run. What kind of interface should I look for? Then you can just use ScaleSim in calculate bandwidth mode, and ScaleSim will tell you that what the optimum bandwidth requirements are. So with that, let me give you a brief overview of how we model gems and convolutions. So this is a very 101 or pedagogical picture of what happens in a gem. So this is a very simple 2 cross 3 cross 3 cross 2 matrix operation. And obviously one row over here gets multiplied with this one. And so we get 4 matrix. The inner dimension is 3 and outer dimensions are 2. So we get a 2 cross 2 matrix, which has 4 elements. And the way to run that in a systolic array would be something like this, that you push the matrix elements of rows of the matrix A from the left side and push the elements of the matrix B from the top side. So you can see over here that each of these columns kind of generate the elements corresponding to these 2 elements here. So so the first row generates first row with the columns of the second matrix coming from the top generates the first row of the output. And if you put the next row from the A matrix in the next row of the systolic array, that row is responsible for generating the second row or the next row of the output. And now if the gem operation is larger, then obviously there is going to be some serialization, and what we essentially have is called tiling. So you can see over here that we take chunks out of the operand matrices and generate a partial partial sums or partial outputs or output elements of the final matrix. So convolutions, I think this Tushar already covered, but I will just cover once more for completeness. That in convolutions, what we do is we slide this window over, slide the filter window over the input image to generate one output image. And then when we do this was a simple example of only one channel, but in real cases, we have multiple channels, and then we also have to accumulate across those channels as well to generate this output image. So that's there. And then we obviously have multiple filters. So each filter, so output generated from each filter in a convolution results in one outer feature map pixel, which basically contributes to its respective outer feature map channel. So in a real scenario, when we have many filters, the output image also has many output channels generated. So this is a simple example of showing that how would we do this convolution operation on a systolic array, which basically converts this convolution into a gem operation and then generates the outputs. So we have this small dummy input feature map and a small filter over here. And first, what we do is we take the first window and then we unroll it. This is typically called the imp to call operation. And then for the next window, when the filter slides, we get one more chunk of input pixels. We take them and unroll them as well and concatenate them in adjacent rows to create an operand input matrix. So now the operation is pretty straightforward, as we have seen in the previous slides. So the filter kind of becomes your second operand. So we unroll the elements of the filter into a vector, and then we pass from the top of the systolic array. So if we have many filters, then we can just add either, if we have more columns of the systolic array, we can allocate those filters onto those columns, or we can wait for serialization and then map the same filter onto the column once the first filter finishes. So this way of mapping is not unique. So there are multiple ways you can do this kind of operation. So what I just have shown in the previous slides is one type of unrolling and mapping when we call that as a data flow, as an output stationary data flow. So this is a blown out picture of what we were doing in the dummy example. So here you can see that there are M filters and we have M columns, and then the input matrix has, when you unroll it, it has 9 rows. So it can fit neatly into a 9 cross M systolic array, like we have shown over here. So as I mentioned before, each MAC is now responsible for generating a particular output pixel, and accumulation of partial sums is now done locally. And as you might have already guessed, that each column generates pixel for a different output channel. It's simply because that each column gets a different filter as its input. So ScaleSim assumes, so this is a ScaleSim fact that it assumes that the output collection is not on the critical path. So if you just track the edges of the inputs and count the number of cycles it takes to do this calculation, you can kind of know what ScaleSim is doing internally. So of course, the maximum usable dimensions in this case is pixels per output channel on the row, and then columns are the number of filters you have. So if you have a larger systolic array, let's say, that would not help with your computation. So another type of mapping or data flow is weight stationary. So in this case, what we do is we, instead of putting each row of the input matrix from the left, we transpose the input matrix and then feed it from the left side. And since it is weight stationary, we pre-fill the weight pixels into the array. So your array will have some sort of register or a latch to store these element of the weight matrix. We put them in, and once the weight matrix is set, we stream the unrolled transpose convolution windows and generate the outputs. So in this case, what happens is that the reduction is done along the rows within a column. And therefore, the critical path now contains time to fill in the weights, the partial sum generation, and as well as the reduction time. And obviously, in this particular case, since we have changed the way things are mapped, the maximum usable dimensions in the rows are partial sums per pixel, and columns are the number of filters. So the reason why I'm talking about the maximum usable dimensions is that when you have an operation, right, you have to choose a data flow, and you want to choose a data flow which maximizes the parallelism so that your serialization steps are minimized, and then you get the most bang for the buck of the hardware we have over here. So these are the things which we need to keep in mind while either we are writing a compiler or we are doing a hand mapping, like in the case of the simulator. So finally, I would like to talk about the third data flow. This is called input stationary, and this is quite similar to weight stationary, as you can kind of get from the name. But the crux over here is that instead of now pre-filling the array with the unrolled weight matrices, we pre-fill the array with unrolled inputs and stream the weights when the inputs are set. So like in the case of weight stationary, however, the reduction is again done across the rows within a column, and critical path also contains the time to fill the input elements, partial sum generation, and final reduction time. And obviously, depending upon the dimension, so depending upon what we have mapped, the maximum usable dimensions are changed as well. This was convolution and gems. So let me talk about the other layer types which we support. So obviously, this is a systolic array, so it is best for doing a gem operation. So anything which can be modeled as a matrix vector operation or matrix operation, like a fully connected layer, is supported. ScaleSim models internally, ScaleSim kind of models it as a convolution, whether you give it as a fully connected layer or another convolution. So it automatically converts into a convolution and then adjusts the dimensions for you. So things which can be formatted in this particular mold, like LSTMs or attentions, are supported. But things like softmax and pooling operations, which has nothing to do with this matrix multiplication motif, they are currently not supported in ScaleSim, although we do have plans to accommodate them as well with the new version we have coming out now. Okay. So now we have talked about inputs, we have talked about how the computations are done. So let me briefly talk to you about the outputs we generate. Um, so we have, so this is a typical console output you would get in ScaleSim. So first the output kind of shows you what you have put as input in the configuration. So it will tell you what the array size is, what data flow you use, what kind of, what are the sizes of your buffers. And then you are using tool in the forced user bandwidth mode, or in a mode where it is supposed to give you the bandwidth requirements or not, and stuff like that. And then it gives you a layer by layer output and some metrics for execution of every layer. So for instance, you can see that it is telling us that, oh, this was in user bandwidth mode with 10 bandwidth of 10 elements per cycle. So you have encountered certain amount of stall, and you have encountered these many compute cycles. And then it tells that what was your mapping efficiency. So mapping efficiency basically means that how much of the array you subscribed for with the mapping. So let's say this was weight stationary, and now we have got pretty good, like 94.53% of the max being actively used for the computation. But because of the stall, the overall utilization we got was something like 23.42%, which was quite low. It shows that um, the whatever configuration this was run on is clearly bandwidth limited. And then it shows that what were the object access bandwidth for the three different operands. And if you look closely into this picture, you can see that most input operands were coming at full rate, like 9.99 words per cycle, which is very close to the bandwidth 10 words per cycle given by the user. So it is obviously waiting for things to come and prefetch before it can start computation. And finally, once all of this is done, it generates traces and the summary files. So the traces and the summary files are kind of look like this. So there are cycle accurate traces for each transaction for the transactions to each level of memory, like SRAM and DRAM, for each operand, which are input feature map, filter, and output feature. So these are cycle accurate in nature. And then we have a few summary files. So obviously, if you are not looking into very close details of each transaction, and you are only interested in high level metrics, then you don't need to generate the traces. You can disable them in the tool and just get the summary files to get all the insight you need. So the summary files are three. So we have a compute report.csv, which captures layer-wise compute cycles, the stalls, which we have just seen that is encountered, the mapping utilization, the overall utilization, etc., which is also shown in the console output. Then we have a bandwidth report.csv file, which gives information about the SRAM and DRAM access bandwidth for each of the operands. So this is a little bit more information than what you get on the console. And then detailed access report gives you detailed information about how many accesses have been done to each of the buffer by each of these memories, what were the timing of those transactions, and so on and so forth. So that's a high level picture of ScaleSim. So we, like Tushar has mentioned before, we have an announcement to make that we are now releasing ScaleSim v2 in beta. So this beta version is released on the ScaleSim project's GitHub, and we are moving to have it quickly reach a stable point so that we can push it to ARM's GitHub. By the way, with the V1 version is still up on ARM, and it is a stable version, and you guys can go ahead and use it, ask questions. We will be happy to get your feedback. So the new features which we have added in this tool is, I probably have already mentioned that it can now work in stall free and bandwidth limited mode. So mapping efficiency, stall count were not reported initially in V1. Now in V2 that support has been added. Code is, we will talk about the code structure later in the tutorials, but what I wanted to highlight is that it is much more modular now. So if you want to change a small thing, you don't have to worry about the entire tool breaking. Um, we, so having a monolithic code is nice and nice because it is controllable, but it's really difficult to make any changes to it. So we changed it there and made it more modular. Also, this entire tool is available as a Python package. So, if you don't want to like go to GitHub, get the code, you really don't care about how the internal workings are, just want to use it in either in your simulator or just for running some of your simulations, you can just install it as a Python package and then call the methods to run ScaleSim directly. And we will show how to do that shortly in the tutorials. And then there are other enhancements coming in the pipeline. We have some planned. We would also like to hear from you at the end of this tutorial. So feel free to tell us what you think about it. And this is a short little advertisement that we have a new website where we will be posting all our updates and how documentation and everything. So if you have a couple of minutes to spare, it would be great if you can go and have a look at the website. So that's the end of my overview. So I will just briefly mention the demos we have. So we will show ScaleSim V2's capability with 3 tutorials. So our first is just using ScaleSim out of the box as a package. No need to change the code or even look at the code, for instance. Then second, what Moritz will be presenting is a short demo on how to add new features, specifically adding a new buffer hierarchy into the memory structure of ScaleSim. And finally, we will talk about using ScaleSim as a library to build bigger simulators so that ScaleSim's compute and memory APIs can do a lot of heavy lifting, which you would otherwise need to do by yourself. So with that, let's hop on to our next session, which is the design space exploration part for using ScaleSim. So if you have any questions, I would be happy to answer. I think we have about 5 minutes. So yeah, feel free to ask any questions. Yes, Mohammed Reza, you can unmute yourself.
Hi. So I put it also in the chat box. So the first question is, do you support like currently multiple batch sizes? Like if I want to change the batch size of the input, is it possible, or you just support one batch sizes? Because I didn't see in the configuration for that there's an option for that. And my second question is about like SRAM. So is it possible in the current version that you, let's say if you want to have multiple bank SRAMs to increase like the throughput, is it possible to change that in the current version, or it's not possible?
Oh, those are very good questions, actually. So first, let me talk to you about batching. So batching is possible in V2 because we have the internals are made to support batching, but we have some bugs coming along, so we have not made it all the way out. So it will be supported in a few weeks. I guarantee you that. So if you are interested, just pull up the V2 code and then just search for batch, like grep for batch size in the tool, and then you can go ahead and set it inside the code. But yeah, I mean, me and Moritz are working to get that out into a configuration file so that you can just use it without any code changes.
What is the default size that currently supported?
It's 1.
Okay.
Default size is 1. Yeah. And second thing about the multiple SRAM banks, so that's a little tricky. So we can add more SRAM banks. So Moritz will tell you about that in tutorial 2, that how to do that. But the tool itself does not. So we do not have a parameter, or right now, if you just run it, right, it would not give you a, internally, we do not have any variable which instantiate multiple things. But that's a good proposal. I mean, that's really a useful thing to have. And so I will look forward to supporting it in the near future. I think there was, does that answer your question?
Yeah, thank you.
Okay. I think there was one more raised hand.
Hi, yeah,
Hi.
11:15. So if you want, I can wait for a little more, and maybe in that 1:30 discussion we can have it. Or do you want me to go ahead?
Sure. I mean, if it is not long, we can answer it and then jump on to the next one.
Well, actually, I wanted to know more about how can we play with the DRAM and SRAM configurations, like change the number of the bands, average latency. If let's say multiple systolic array are there, then give higher priority to one of them over the other for requests and everything to see if
Oh,
we can.
that's Oh, okay. That is a good question. So hold that thought. Maybe after these two tutorials, right? The modifying ScaleSim to adding more a different buffer hierarchy, and then I will also talk about the scaled out simulator in the third tutorial. So
Mhm.
after that, maybe you will have better idea, and then if you stick around, then we can have a detailed discussion at from 1:30 to 2.
Sure.
But thank you for your
Sure.
for those
And
suggestions.
apologies, I didn't got time to read about ScaleSim version 1, but by any chance, do you guys have some kind of correlation number with RTL or ASIC for same kind of configuration to see
We
how?
do. We did some validation in our ISPAS paper, but we do not have any RTL which is like public, which we validated with. So it was our internal implementation of systolic arrays, and we matched the cycles.
Oh,
So you can read about it in our ISPAS paper.
got it.
Uh,
Thank.
okay. Okay. So then let me move to the next, to my next thing. So let me stop sharing for a bit and then start video recording once more so that I have a nice clean cut video. So yeah, I will be there in a minute.